So, you've been hearing a lot about big data. It's this massive, ever-growing force that's reshaping industries. And right at the heart of taming that beast is a tool called Spark. But for a lot of us who live and breathe Python, the entry point is PySpark. It's this super powerful open-source framework that lets you process huge datasets across clusters of computers, all using the Python syntax we already know and love. It's become the go-to for data engineers, data scientists, and analysts who need to wrangle terabytes of data without breaking a sweat. It's fast, it's scalable, and honestly, it's pretty elegant once you get the hang of it. Because it's so popular, it's also a hot topic in technical interviews. Companies are looking for people who can not just talk about big data, but can actually work with it effectively. That's where this video comes in. I've been in your shoes, scrolling through job descriptions, prepping for those high-stakes interviews. So today, we're going to break down the top 10 most common, most crucial PySpark interview questions. We're not just going to list them, we're going to dive into the why behind them and walk through practical, real-world code examples for each one. My goal here is simple, to give you the clarity and confidence you need to walk into your next interview and just nail it. By the end of this video, you'll have a solid foundation, a clear understanding of the core concepts, and the practical code skills to back it up. We're going to cover everything from the basics to some of the more nuanced features. So, grab your favorite editor, get ready to code along, and let's get you ready to ace that PySpark interview. Alright, so kicking things off with question number 1, the one you're almost guaranteed to get: what is PySpark? It sounds simple, but your answer here sets the tone for the entire interview. You want to show that you understand not just the what, but the why. So at its core, PySpark is the Python API for Apache Spark. Think of it as the bridge that connects the simplicity and rich library ecosystem of Python with the raw distributed computing power of Spark. It lets you write your data processing logic in Python, and then Spark takes that logic and executes it in a parallel, distributed manner across a cluster of machines. The main reason it's so popular is that it democratizes big data processing. Before tools like Spark, handling terabytes of data was an incredibly complex task, often reserved for developers with deep expertise in Java or Scala and distributed systems. PySpark lowers that barrier to entry significantly. If you know Python, which a massive number of data professionals do, you can start working with big data. It combines the ease of use of Python with the high performance of Spark's engine, which is written in Scala and runs on the JVM. This combination is a game changer. So what are its main features? First up is speed. Spark's engine performs in-memory computation, which can be up to 100 times faster than traditional map-reduce systems that write intermediate results to disk. Second is scalability. You can run PySpark on a single laptop for development, and then scale that same code to run on a cluster with thousands of nodes without changing the logic. It's built for growth. Third is its unified analytics engine. Spark isn't just for simple data processing. It includes libraries for SQL and DataFrames, machine learning, graph processing, and real-time stream processing. When you're answering this in an interview, you want to hit these key points. Mention that it's the Python API for Spark. Talk about how it makes big data accessible to Python developers, and definitely highlight its key features: speed through in-memory processing, scalability from a single machine to a large cluster, and its comprehensive unified ecosystem for various data tasks. That shows you have a well-rounded understanding. It's not just a tool, it's a full platform for big data. Ultimately, PySpark is used because it solves a critical problem. It makes processing massive datasets manageable, efficient, and accessible. It allows teams to iterate quickly, build complex data pipelines, and run sophisticated machine learning models on a scale that would be impossible with traditional tools like pandas on a single machine. It's the bridge between data science and data engineering, and that's why it's such a valuable skill to have on your resume and in your toolkit. Moving on to question 2, which gets a bit more practical. How do you create a Spark session? This is the fundamental starting point for any PySpark application. You literally can't do anything in PySpark without it. The Spark session is the entry point to all of Spark's functionality. Think of it as the driver's seat of your car. You have to get in and turn the key before you can go anywhere. It's the object that controls your Spark application, manages the cluster resources, and provides the methods needed to create data frames and execute your code. So, how do you actually create one? The code is surprisingly straightforward. You start by importing SparkSession from the PySpark.sql module. Then you use a builder pattern to construct the session. It looks something like this: SparkSession builder app name, my app name, get or create. Let's break that down. SparkSession.builder initializes the builder object. App name is a configuration method where you give your application a name, which is super useful for identifying it in the Spark UI or logs. It's a good practice to always name your apps. The final piece, get or create, is the magic part. This method checks if a Spark session already exists in the current context. If it does, it returns that existing session. If it doesn't, it creates a new one based on the configurations you've provided. This is incredibly useful because it prevents you from accidentally creating multiple Spark contexts in the same application, which can cause all sorts of issues. It makes your code more robust and reusable, especially in environments like notebooks where you might rerun cells. In an interview, after showing the code, you should explain why it's so important. The Spark session encapsulates the Spark context, SQL context, and Hive context, which were separate entry points in older versions of Spark. By unifying them, the Spark session provides a single, clean interface for interacting with all of Spark's features. It's how you configure your application's properties, like the amount of memory for the driver and executors, the number of cores, or any other Spark-specific settings. You can chain multiple .config methods before the .get or create call to set these properties. So, to summarize for your interviewer, you create a Spark session using its builder pattern. You import it, call SparkSession.builder, set an application name with app name, add any other necessary configurations with .config, and then call .get or create to either retrieve an existing session or instantiate a new one. It's the gateway to the entire Spark ecosystem, and knowing how to properly initialize it is the first step in writing any PySpark job. It's a foundational piece of knowledge they expect you to have down cold. Alright, question 3 is a big one that gets to the heart of PySpark's data structures. What are RDDs and data frames, and what's the difference? This is a classic concept check. Your ability to answer this clearly shows whether you've just memorized some syntax or if you actually understand how Spark works under the hood. Let's start with the original, the RDD, or Resilient Distributed Dataset. This was Spark's primary API when it first launched. An RDD is an immutable distributed collection of objects. It's essentially a low-level API that gives you a ton of control. You can think of an RDD as a distributed list of Python objects. It's resilient because it keeps track of the lineage of transformations used to build it. So if a partition of data is lost, Spark can automatically recompute it. It's distributed because the data is partitioned and processed across the different nodes in your cluster. RDDs are schemaless, meaning Spark doesn't know what kind of data is inside them. This gives you flexibility. You can store any type of Python object, but it comes at a cost. Without a schema, Spark can't optimize your operations as effectively. This is where the DataFrame comes in. Introduced later, the DataFrame is a higher-level API built on top of RDDs. A DataFrame is also an immutable distributed collection of data, but it's organized into named columns, just like a table in a relational database or a pandas DataFrame. This structure is the key difference. By imposing a schema, a known structure with named columns and data types, Spark gains a much deeper understanding of the data. This allows it to perform significant optimizations behind the scenes using a component called the Catalyst Optimizer. So when do you use which? For over 95% of use cases, you'll want to use data frames. They are easier to work with, the code is more readable and concise, and most importantly, they are significantly faster due to the catalyst optimizer. Operations like filtering, joining, and aggregating are much more important. the DataFrame API abstracts away. It's like driving an automatic versus a manual car. The automatic or DataFrame is easier and more efficient for most trips, but a pro driver might want the manual or RDD for a specific race. For a code example, you can show creating an RDD with spark.sparkContext.parallelize on a list of data, then show creating a DataFrame from that same list using spark.createADataFrame. Visually, the RDD might just look like a list of tuples, while the DataFrame will have clear column headers. This simple comparison makes the abstract concept concrete. Your answer should emphasize that DataFrames are the modern preferred API due to their performance optimizations and ease of use, while RDDs are the powerful, low-level foundation they are built upon. Alright, question 4 is a bread-and-butter task you'll do all the time. How do you read a CSV file into a DataFrame? This is a practical question designed to see if you can handle the most common data ingestion task. Fortunately, PySpark makes this incredibly easy and powerful. The main tool you'll use is the DataFrame Reader API, which you access through your SparkSession object. The syntax is clean and fluent, making it very readable. You start with. From there, you specify the format you're reading. In this case, it's a CSV, so you'll chain, or more commonly, just use the shorthand method. So the core of the operation is. This simple line is enough to get started, but, in the real world, CSV files are rarely perfect. That's where the options come in. And mentioning these options in an interview shows you have practical experience beyond a simple tutorial. For example, what if your CSV has a header row? If you don't tell Spark, it'll just read the header as a data row. To handle this, you add the option. This tells Spark to use the first row as the column names. Another common issue is data types. By default, Spark will infer all columns as strings when reading a CSV. To get proper numeric and date types, you can add. This tells Spark to make an extra pass over the data to figure out the best data type for each column. While it's convenient for exploration, it can be slow for very large files. For production jobs, a more robust approach is to define the schema yourself. You can create an object that specifies the name and data type for each column and pass it to the reader using the method. This is honestly the most efficient and reliable way to read data, as it avoids the overhead of schema inference and prevents any unexpected typecasting errors down the line. It's a pro tip that interviewers love to hear. So a complete production-ready example would look something like this. First, define your schema using and then use. In your answer, you should walk through this progression. Start with the simplest, then introduce the and options to handle common scenarios, and finally, present the explicit schema definition as the best practice for performance and reliability in production environments. This shows a deep and practical understanding. Now we get to the core of data manipulation with question 5. How do you perform filtering and aggregation in PySpark? This is where you transform raw data into actual insights. These are two of the most fundamental operations in any data analysis workflow, and PySpark's DataFrame API provides a powerful and expressive way to do them. Let's start with filtering. Filtering is all about selecting a subset of rows from your DataFrame based on a condition. The two most common methods for this are and. They are completely identical in function. Which one you use is purely a matter of style preference. To use it, you pass a condition to the method. This condition is expressed using column objects. For example, if you have a data frame of sales data called and you want to find all sales greater than $100, you would write. Notice how you reference the column and then apply a standard comparison operator. You can also build more complex conditions using for and, for or, and for not. For instance, filtering for sales over $100 in the electronics category would be. Next up is aggregation. Aggregation is about summarizing your data. This usually involves an operation followed by an aggregate function like OR. The method groups the data frame by one or more columns. All the rows with the same value in the grouped column are collected together. Then, you apply an aggregation function to calculate a summary statistic for each group. For example, to find the total sales amount for each category, you would write. This returns a new data frame with two columns, category and sum amount. You can also perform multiple aggregations at once using the method. For instance, to get the total sales and the average sale amount per category, the code would be. However, since you can't have duplicate keys in a dictionary, a better way is to use the module. You'd import and so on and write. Using is key for giving your new aggregated columns clean, readable names. In an interview, you should be ready with a practical example that combines both filtering and aggregation. For example, first, I would filter the DataFrame to only include data from the last year. Then, I would group the filtered data by product category and calculate the total sales and number of unique customers for each. This shows you can chain these operations together to answer complex business questions, which is exactly what these tools are for. It demonstrates a workflow, not just isolated syntax. Question 6 delves into a core concept that makes Spark so efficient. What is lazy evaluation? This is a key differentiator for Spark, and understanding it is crucial. Lazy evaluation means that when you tell Spark to perform a transformation on a data frame, it doesn't execute it right away. Instead of immediately running the command, Spark builds up a logical execution plan. It's kinda like giving a chef a recipe. The chef reads the whole recipe first before starting to cook, looking for ways to be more efficient. So when you write code like, Spark doesn't actually filter the data, then group it, then aggregate it in separate steps. It simply records these transformations. It creates something called a directed acyclic graph, or DAG, which represents the sequence of operations you've requested. Each transformation you call adds another step to this plan. Spark waits until you call an action before it actually executes anything. What's an action? An action is an operation that requires a result to be returned to the driver program or written to an external storage system. Common actions include, which displays data on the console, which brings all the data back to the driver as a list, which returns the number of rows, and which saves the output to a file. It's only when one of these actions is triggered that Spark looks at the entire DAG of transformations you've built. This is where the magic happens. Before executing the plan, Spark's Catalyst Optimizer analyzes the DAG and figures out the most efficient way to perform the computation. It can reorder operations, combine transformations, a process called pipelining, and optimize the physical execution on the cluster. For example, if you filter a dataset and then select only a few columns, the optimizer is smart enough to know it should push the filter down to the data source, so it reads less data from the disk in the first place. This is a massive performance gain. So, to explain this with a simple example, imagine you have a large log file. You write code to read it, filter for rows containing error, and then count them. Then, and finally, the reading and filtering are transformations. Nothing happens yet. The is the action. Only when you call does Spark actually go to the file, read the lines, filter them for error in a single pass, and count them up, without ever creating the intermediate in memory. Lazy evaluation, combined with the optimizer, is what makes PySpark so fast and resource efficient. Question 7 is another very practical one, dealing with the messy reality of real-world data. How do you handle missing data in PySpark DataFrames? No dataset is perfect, and null values or NaNs are something you will constantly encounter. Knowing how to deal with them cleanly and efficiently is a critical skill for any data professional. PySpark provides a dedicated API, which you can access through the attribute of your data frame. So, this API contains a set of specialized functions for handling null values. The two main strategies for dealing with missing data are dropping it or filling it. Let's talk about dropping first. The method allows you to remove rows that contain null values. In its simplest form, we'll remove any row that has a null value in any of its columns. This can be a bit aggressive, as you might lose a lot of data, so you can control its behavior. For example, we'll only drop rows where all values are null. You can also get more specific. We'll keep rows that have at least 2 non-null values. This is useful for keeping rows that are mostly complete. Even more useful is the parameter. We'll only check for nulls in the email and phone columns and drop rows if a null is found there, ignoring nulls in other columns. This gives you precise control over your data cleaning process. The second strategy is filling or imputing the missing values. The method is used for this. You can fill all nulls with a single value, like which would replace all numeric nulls with 0. It's smart enough to only fill columns of a compatible type. If you pass a string like, it will only fill string columns. For more granular control, you can pass a dictionary too. For example, we'll replace nulls in the age column with 30 and nulls in the city column with unknown. In an interview, it's good to discuss the pros and cons. Dropping data is easy, but can lead to a loss of information and potentially biased results if the missingness is not random. Filling data preserves your sample size, but requires a thoughtful strategy. Filling with the mean, median, or mode is a common statistical approach. You can even use more advanced techniques, like building a machine learning model to predict the missing values. Mentioning that you'd first analyze the extent and pattern of missing data before choosing a method shows that you think like a data scientist, not just a coder. Alright, question 8 covers another cornerstone of data manipulation, straight from the world of SQL. How do you join two data frames in PySpark? Combining data from different sources is honestly a daily task in data engineering and analysis. PySpark's join capabilities are, well, pretty extensive, and they're designed to be both powerful and familiar to anyone who's worked with databases before. The primary method you'll use is the method on a data frame. It takes the other data frame you want to join with, the join condition, and the type of join. The basic syntax looks like this. Let's just break this down a bit. Means you're joining with. The second argument is the join condition. Here, we're matching rows where the ID column in is equal to the user_IDE column in. This is, honestly, the most common type of join key you'll see. You can also specify multiple columns for a composite key by stringing them together with an. The third argument, inner, specifies the type of join. PySpark supports all the standard SQL join types, and you should really be able to name and explain them. The default is an inner join, which returns only the rows that have a matching key in both data frames. A left join, or left outer, returns all rows from the left data frame, and the matched rows from the right data frame. If there's no match, the columns from the right data frame will just be null. A right join is, well, the opposite. And a full underscore outer join returns all rows from both data frames, filling in nulls on either side where there isn't a match. There are also some more specialized joins. A left underscore semijoin is kind of like a filter. It returns only the rows from the left data frame that have a match in the right one, but it doesn't include any of the columns from the right data frame. It's an efficient way to check for existence. Conversely, a left underscore anti-join returns only the rows from the left data frame that do not have a match in the right one. This is super useful for finding records in one table that are missing from another. One common issue with joins is duplicate column names. If both and have a column named date, the resulting data frame will have two date columns, which can get confusing. The best practice is to rename or drop the ambiguous column after the join. When you're explaining this in an interview, it's great to have a simple example ready, like joining a data frame with an data frame on. Walk through how an inner join gives you users who have placed orders, and a left join gives you all users, showing null for orders placed by users who haven't bought anything yet. This practical scenario really helps the concept stick. Getting close to the end, question 9 is actually the reverse of question 4. It's about getting your results out of Spark. How do you write data from a data frame to a file? After all your hard work cleaning, transforming, and analyzing the data, you need to save the result. This could be for a report, for another system to consume, or for long-term storage. Similar to reading data, PySpark provides a clean API, which you access through the attribute of your data frame. The structure is very similar to the reader. You start with your final data frame, then access the writer with. You specify the output format using, and then call with the destination path. Just like with the reader, there are convenient shorthand methods, so instead of, you can just use. For example, let's talk about formats, because this is a key part of the answer. You can write to many formats, like CSV, JSON, and text files. But in the big data world, columnar formats like Parquet and ORC are king. When an interviewer asks this question, they're often listening to see if you mention Parquet. Parquet is an open-source, columnar storage format that is highly optimized for the kind of analytical queries Spark performs. It stores data by column, which leads to better compression and massive performance improvements for queries that only need a subset of columns. Since you can skip reading the data for columns you don't actually need, the Writer API also has modes for handling situations where the output directory already exists. By default, if you try to save to a path that already exists, Spark will throw an error to prevent you from accidentally overwriting data. You can control this with the method. For example, we'll delete the existing data before writing the new data. We'll add the new data to the existing files, and we'll simply do nothing if the path already exists. Another important concept to mention is partitioning. When you're writing a large dataset, you can partition it based on the values in one or more columns using the method. For example, we'll create a directory structure like. This is incredibly powerful because it allows Spark and other query engines to prune entire directories of data if a query has a filter on the partition columns, dramatically speeding up reads. Mentioning partitioning really shows you're thinking about performance and scalability, not just saving a file. And for our final question, number 10, we're looking at how to extend Spark's built-in functionality. How do you use UDFs, or user-defined functions, in PySpark? While Spark has a massive library of built-in functions sometimes you have a very specific piece of business logic or a complex transformation that isn't covered. This is where UDFs come in. A UDF allows you to define your own function in standard Python and then apply it to a DataFrame column. The process involves two main steps. First, you write a regular Python function that takes one or more inputs and returns a single value. This function contains the custom logic you need. For example, let's say you want a function that categorizes a product's price into low, medium, or high. You would write a Python function that implements this logic. It's just plain Python, which is what makes UDFs so accessible. The second step is to register this Python function as a PySpark UDF. You do this using the function from. When you register it, you must also specify the return type of the function using PySpark's data types, like OR. This is crucial because Spark needs to know the schema of the column the UDF will create. So the registration looks like this. Once your UDF is registered, you can use it just like any other built-in Spark function. You apply it to a column to create a new column using the method. For example, this will take each value from the price column, pass it to your Python function, and store the result in a new column called price_category. It's a powerful way to integrate complex custom logic directly into your Spark transformations. However, it's critical to mention the performance implications in an interview. While UDFs are flexible, they come with a significant performance cost. When Spark encounters a UDF, it has to serialize the data from the JVM, send it over to a Python process to execute your function, and then serialize the result back to the JVM. This back-and-forth movement and serialization overhead can be a major bottleneck. The Catalyst optimizer also can't see inside a UDF, so it can't optimize the logic within it. Therefore, the strong recommendation is to always try to use Spark's built-in functions first. They're written in Scala or Java and operate directly on the JVM, making them orders of magnitude faster. UDFs should really be your last resort when there's no other way to express your logic. So there you have it, the top 10 PySpark interview questions, broken down with the concepts and the code you need to know. We've covered everything from the fundamentals like creating a SparkSession and understanding RDDs versus DataFrames, to the practical, everyday tasks of filtering, joining, and handling missing data. We even touched on advanced concepts like lazy evaluation and the trade-offs of using UDFs. The key takeaway is to not just memorize the syntax, but to understand the why behind each concept. Why are data frames preferred? Why is lazy evaluation important? Answering those questions is what really separates a good candidate from a great one. Now, the most important step is up to you. Watching this video is a great start, but the real learning happens when you get your hands dirty. I highly encourage you to take these examples, spin up a PySpark session on your own machine, and play around with them. Try them on your own datasets. Break the code, fix it, and try to solve a problem using a combination of these techniques. That hands-on practice is what will truly solidify these concepts in your mind and give you the confidence to talk about them fluently in a high-pressure interview situation. I genuinely hope this has been helpful and has armed you with the knowledge you need to go out there and land that dream job. Best of luck with all your upcoming interviews. If this video helped you out, a like would be awesome. And make sure you're subscribed for more content like this. And I'd love to hear from you in the comments. Let me know if you've encountered other common PySpark questions in your interviews or share your own experiences. Let's help each other learn and grow. Thanks for watching, and I'll see you in the next one.